Thank you. My name is Bálint Tóth. I am from the University of Pannonia. I'm a PhD student, and I would like to talk about the low-level CUDA optimization of the previously mentioned uh, plasma simulators Poisson equation solver. I would skip the introduction because the previous talk by Zoltán has practically covered all the context of my work. But before I start, I will be saying grid a lot of times. During this talk, I want to clarify a bit the nomenclature. When I say grid, I will usually refer to the multigrid or the discretized Poisson equations lattice. If I explicitly mention, then I'm GPU grid, then I will be talking about the grid from the CUDA programming model, which is the way of writing general purpose code for NVIDIA GPUs. Grid is made up of blocks of threads. But yeah, this is where we start practically with the two-dimensional Poisson equation for electric field. More specifically, the discretized version using finite difference method with these 5-point star approximation when we practically rewrite the partial differential equation into a difference equation using describing each point with the neighboring other grid points. And from this point, it turns into kind of what numerical method would be the best for solving this problem. Of course, we can rewrite it as a system of equations, a linear system of equations, and use Gaussian elimination or some other textbook method. There are also well-known iterative methods such as Jacobi iteration and Gauss-Seidel iteration. There are fundamental problems with all of them that would prohibit use in this plasma simulation environment. Gaussian elimination, of course, is order n cubed asymptotic runtime. It is very slow, and these primitive iterations, such as even the successive over-relaxation, would require hundreds of thousands of iteration steps, and it would be just impractical. So we turned our attention to first spectral solvers that I will cover later in this talk, and the multigrid algorithm. I would also like to mention that there are pre-made, readily available algebraic multigrid implementations as well as pentadiagonal solvers, because if we write this difference equation as a system of linear system of equations, it will turn into a block tridiagonal, i.e. a pentadiagonal system. And there are direct methods for solving that, but it's again unsuitable for our simulation because that would require excessive data manipulation. We would like to solve everything on the same grid that we use for the rest of the simulation without, memory copies, because modern GPUs are all memory bound. So we want to keep things concise. And this is how the multigrid comes into place, because it could be executed directly on the grid itself. The basic idea behind multigrid is simple iterative solvers, such as Jacobi and Gauss-Seidel, have this smoothing property, meaning that after a couple of iterations, they will produce a smooth result. So if we take the error from the actual solution of the system, we will end up with a very smooth error curve. And if we analyze this error in frequency domain, we will see that the kind of high frequency components of the error are eliminated first, and only the low frequency components remain. So if we average some and leave out some grid points and coarsen our grid, that low frequency error will be relatively high on this grid. Meaning if we do the smoothing again and reduce the system until we get a single point, the solution becomes trivial. And from that point, we can build up to the smoother grid using interpolation. And this is the basis of the multigrid V cycle. There are other cycles like FW. We implemented the V cycle. And we started out with a sequential C++ implementation that was subsequently transformed into a CUDA implementation by replacing steps of the V cycle using GPU kernels, initially with manual host device memory copies, and later keeping all the memory in a fixed set workspace and only calling the kernels from the host side. Now, what we can see here is a trace diagram of our implementation. In the different rows, you can see the kernels, and these little blue trace marks indicate how long they took on the GPU. And this is exactly how far you would get if you just download a geometric multigrid from GitHub and use it. It's mostly just calling kernels from a for loop. And especially in this red region, we can see that the GPU is, well, idle for the most part. The kernels are very short. And note that the multigrid reduces the entire problem into a single point, meaning that at some point we are starting up an entire CUDA kernel for a single item. So we can drastically improve it using a kernel fusing technique that I have implemented. The main limitation with the base implementation is that each step needs to run in sequence. So we need synchronization that can only be achieved from the side by launching another kernel and waiting for the kernel to finish. And if we have multiple thread blocks, i.e. we have a large GPU grid, then we couldn't really synchronize from the device's side, so from the kernels. However, due to multigrid reducing everything at some point below a 32 by 32 lattice, we can actually, in a single block, use device-side initiated synchronization, meaning the entire part of the V cycle below a 32 by 32 grid can be implemented in a single block. And it achieved almost 10 times speed up compared to the multiple block version or multi-kernel version. And as you can see on the trace, drastic runtime improvements, and the GPU utilization jumped up to like 80%. This is really good. We don't want our GPU to idle. And after some benchmark measurements, we can see that for, sorry, spoilers, for relevant grid sizes for plasma simulation, compared to the C++ baseline, on different GPUs, we have achieved from around 4 times to 44 times speed up for a single multigrid V cycle. Of course, this doesn't really solve the equation. We will need to run around 20 V cycles, but it's still much better than using the original solver from the code base. It is around a modest 6 times speed up compared to that, actually, which, well, got us into the point where the visualization from the previous presentation can actually be executed on a laptop. Well, we can go even further. The original implementation used a sign transform-based spectral method, and I'll spare you the boredom of these formulas. The main idea is that if we transform the entire grid to sign transform domain, the entire solution step is going to be a single operation, which is really good. But how do we get to the sign transform domain? Well, we can do the order n squared runtime naive approach, or we can use fast Fourier transform algorithm because, well, again, the mathematics is a bit irrelevant now, but if we extend our functions, grid, we essentially copy the grid in the horizontal axis and flip it, i.e. multiply it by -1. The resulting signals, two-dimensional Fourier transform, will equate to 2i times the sine transform. So essentially we get the very basic algorithm of doing a sine transform with Fourier transforms, compute the solution in a single kernel, and then copy back everything, transform back everything using Fourier transforms. And these parts here are implemented as kernels, and the QFFT marked lines use the NVIDIA supplied QFFT library, or obviously a very good optimized fast Fourier transform. And everything runs in a CUDA grid, graph, another G word. Everything runs in a single CUDA graph, so it's essentially a single GPU call to execute the entire transform. There was a bit of a need for some trickery with the memory layout. This is the memory mapping or buffer mapping for a single sine transform. In the first stage, we really just copy and flip the grid to the vertical axis, do a batch fast Fourier transform, and do the same thing for the other axis. It is just a very fancy two-dimensional Fourier transform. A bit about the API for the software people here. We use a predefined kind of configuration structure to describe the hyperparameters of the algorithm, and we also use a workspace structure to manage all the buffers and GPU side resources. So the whole point is that this solve function can be called in a simulation loop given the workspace, which can be, of course, connected to external data pointers. So we can directly operate on the simulations grid. And both solvers use the same function naming. It's just resolved in compile time with some C++ argument-dependent lookup. And with this heavily optimized spectral solver, we have achieved on an A100 GPU a speedup of 17 to 20 compared to our previous best approach, which is running 20 CUDA V cycles. And compared to the original implementation, the baseline, we have achieved like 100 times speed up in the solver itself. And the solver originally was half of the total execution time of the simulation. So it provided us with some drastic runtime improvements. And I'd like to quickly summarize. So we have designed and implemented our own in-house two-dimensional discrete Poisson equation solvers. We have achieved relatively high speedups compared to host side, sequential C++ and MATLAB benchmarks. And we have beaten our own multi-grid implementation with this spectral solver. There are still some bugs I have to iron out and further developments, such as actually implementing a convergence test for the multi-grids iteration. And much like the fast Fourier transform, there could be, one could implement a direct fast discrete sine transform. But for our current uses, this method is sufficient. And with that, I would like to thank your valued attention. And if you have any questions, I'm looking forward to answering them. Thank you.
Is there any question for Bálint and Zoltán, since it is a joint question?
Yeah, my memory only spans one talk, so so in this comparison between the spectral method and the multigrid method, this is a quite large difference that you are showing. Have you managed to completely understand what is the difference coming from? So is this a numerical, a discretization thing that somehow the multigrid method is not efficiently communicating the time evolution or the evolution in the iteration information from one end of the grid to the other, that is the spectral method is doing more efficiently? Or is this just coming from scheduling issues on the GPU that the multigrid is somehow not that well fitting or well using the GPU? So how much is it software related and how much is it numerical related? Speed.
I would say they go hand in hand because currently the main kind of weakness of the multigrid is that I couldn't fit the entire workspace into shared memory. So there still need to be global memory operations. I still need to execute a whole bunch of global memory round trips with the multigrid, and the Spectra could just cache it. That's one thing. Well, I didn't really spend a long time tweaking the multigrid. So there could be better hyperparameters for it. And I think there's another part of this answer. May I walk over a bit, mine?
Just some addition. So obviously, the main problem is the grid is very small, so we don't have enough parallelism to use the GPU, and the FFT is just log n complexity. In the multigrid, we still have to do the Jacobi iteration, so the complexity is worse. But that's the main difference. We hope that for larger grids, it will be a bit different.
And one of the other things I was pondering is what was the target architecture or feature set? Because in the recent enhancement, both in hardware and the CUDA API, are giving us much more control over synchronization, communication between thread blocks. Like these thread blocks can access each other's shared memory in some cluster. So I wonder if all of these or some subset of these can be used to help with the multi-grid method also in this endpoint where you need to communicate a lot.
Yes, the cluster is not available on the A100, the cluster programming API. We hope to move the code to the Hopper GPUs where we can test the cluster part and distributed shared memory.
Okay.
Well, there is one other feature that we actually have is the dynamic parallelism API.
That would be my other question.
Yes, I haven't arrived there, but it's on the to-do list. I'm actually hoping it would help. Well, I did some benchmarks for these kind of similar kind of problems, and the global synchronization part in the dynamic parallelism didn't really perform well. However, the launch overhead of the subkernel starts were much better. So I'm hoping improvements from it.
Was that with or without using graphs?
Sorry?
CUDA graphs. Was that with or without?
Without.
Yeah, because they also combine and you need to test whether using dynamic parallelism with graphs is better or not than leaving out the dynamic parallelism. We had some benchmarks where it also didn't add much to the improvement by using dynamical parallelism because we feel it's more a convenience feature. But
okay.
I had limited experiments.
The dynamic parallelism, I'm not sure. In this version, I'm using graphs.
Graphs
so
definitely help.
That's
great. Yeah.
They do.
Thank you.
Yeah, So on the previous presentation, there was a mention that the scaling of the GPU like flattens out. What was the main bottleneck here? Was it like mostly just the communication between the GPUs, or was there some other element here?
It's mainly the communication. Yeah.
Okay, and it was so it was actually hitting the bandwidth limit of the PCIe bus.
Sorry, I didn't get that.
Was it like hitting the transfer limit on the like the PCIe bus, or?
No, the data size is very small.
Okay.
So I think it's more inefficiency, but
Yeah, there's another part to that. The GPUs got saturated, or I mean, sorry, they didn't get saturated. So when the particle count drops below what we have measured at around 1.5 million, then we kind of max out the GPU's performance and it wouldn't increase anymore. The communication only involves the 255 by 255 grid each time in doubles. So it is kind of constant throughout the single node execution.
Okay, thank you.
maybe just a last comment. So with all this optimization, we now basically eliminated the Poisson solver problem, and we introduced a new one. Now the density calculation is a dominating factor. So we will have to continue and optimize that. And then maybe we get a third one to optimize. So it's a never ending story. Yeah.
Is there any more questions? Then, as I didn't see any other ones, thanks for Bálint and Zoltán for their talks.
Thank you for having me.